today we are going to just try to put together everything that we've learned about matching networks, so to help you to put it in, classify it in your memory and be able not to get confused, because it is easy when you present a lot of different approaches to really get confused about it. So what I try to do in this document that does not supersede everything else, all right? It's just like a summary of what we have looked at so far. So matching networks, what is it that we have learned about matching networks? First of all, the first thing we've learned was the quarter wave transformer. But you need to remember the quarter wave transformer works when you have a real load and you want to match it to, and you want to transform it to another real value, all right? So that's why it's called a transformer. It is from a real load, any type of real load, you can transform it to any type of real value, all right? Now, when I say real value, what I really mean is to another real impedance, from a real load to a real impedance. If you want to match this real load that they give you to a source, as we will see below in the explanation, then you really have, as we discussed about how you get the maximum real power out of the source, then you have to match your load to the real internal impedance of the source. You cannot match your using a quarter wave transformer, a real load to a complex internal impedance of the source. You cannot match a complex load to a real internal impedance of the source. You can only match real to real, all right? So that's what you need to keep in mind. And how do we do this? By selecting the length of that section of line that we put between the load and the source, and also by selecting the characteristic impedance. It's called quarter wave because the length is a quarter of a wavelength. And the characteristic impedance for this section of line, that is the quarter wave transformer, and out of this square root. All right, so that is there. So if I ask you, or anybody else for that matter, if they give you this problem where you have a real load and a real internal impedance for the source, you should not even think about anything else, but immediately go to a quarter wave transformer. All right. What are the cases where you cannot use it, even if it's a real load to a real impedance? If for some reason I have introduced additional restrictions, all right? So one could be that you have to have a characteristic impedance of some kind of particular value that does not really agree with the square root of your load to whatever impedance or the internal impedance of your source. In that case, you're constrained, all right? The other constraint can come from the length of the line. If somebody tells you, yes, you can use the length of the line, but it has to be this length, then you can be a little smart and do a couple of things. If the length they give you is longer than a quarter of a wave, all right? So you use the space for a quarter of a wave to create a transformer, and then the rest of the line does not matter. You will see that as we go further. But so we don't go over too many things. Remember, from a real load to transform it to a real impedance quarter of a wave, at least for this class, all right? Beyond that, you need to know that there are restrictions. But for this class, if I give you any problem like that, you need to consider the quarter wave immediately. Now, here is an example. Let's assume that we have a real load here of 100 ohms, and we want to connect this through a section of a line We have not given restrictions to the length or to the characteristic impedance. And we want to connect this to a source that has an internal impedance of Z naught, which is 50 ohms, all right, here. To match this load to the internal impedance of the line, of the source, then we need to use the quarter wave in length, and Z1 is the characteristic, is the square root of the load you want to transform these two. So you want to transform 100 ohms to 50. So that 50 times your load, square root, right? And that gives you 70.7 ohms. So I can take a quarter of a wavelength line of 70.7 ohms characteristic impedance, and that is going to match perfectly. 100 ohm load to 50 ohm. Now, in this particular design, I do not have to give you the frequency, since you can express all of your dimensions into electrical lengths. An electrical length is a dimension in terms of a wavelength, all right? So if I don't give you a frequency, then that's where you stop. You say quarter of a wavelength. If I give you a frequency, then from that frequency, you can calculate lambda. And I told you to remember that 1 gigahertz is 30 centimeters. And then you can scale up and down, all right? 10 gigahertz, 3 centimeters. 100 megahertz, 300 centimeters. So that's how it goes. Now, if I give you a frequency, then you can find how much is the wavelength, and then you can find the dimension, which is a quarter. You can find it in physical length, in units, all right? Of a centimeter, meter, whatever you choose. All right, so that is the first example. Second example. As I told you, they said in this particular case, they give you this, and then they tell you that I have a line already connected to my source. And this line that I already saw, your source comes together with a line, all right, practically, that you have to connect to, and that line is 50 ohms. That's the, right? So there is one small constraint that you have. You don't go directly to the source, but you have this line to deal with. Okay. What do you do in this particular case? You still have to add something between this 50 ohm line and your load, because if you put your load to this 50 ohm line, it does not matter what length it is. If you put this load, this 50 ohm line, then you have a mismatch. All right, it's going to create a reflection coefficient here if you place your load directly to BB prime. So we have to add something between this section of the transmission line that they give you and this load. What do we add? A quarter wave transformer. Why is that? Because even if I have a section of a line, to match to my source and the line is part of it, I have to transform this 100 ohm load to 50 ohms here at BB prime. Because if my load there becomes 50 ohms, then my reflection coefficient on this line becomes 0 at BB prime. And because it's 0 at one point, there's going to be 0 everywhere. Remember we said that? We said the magnitude of the reflection coefficient is the same everywhere on the line. So if it's 0, magnitude 0 is 0 everywhere on the line. All right? Now, if I match therefore here, I'm done. I match to my source. If this is 0, how much is your VSWR? 1. You need also to remember that. You need to remember that VSWR is 1 plus magnitude of gamma divided by 1 minus magnitude of gamma. When gamma is 0, VSWR is 1, is the smallest value you can get. When gamma is 1, VSWR goes to infinity, which is becomes practically, it says that it can get very large values. And the larger the BSW are, the worse is the match. I mean, the bigger the mismatch, rather, if you want to say. All right, so in this particular case, we did this. We included a quarter wave. We did a match here. And now this section of the red line can have any length. The length can be determined by somebody else, by whoever designed the source for you, because for those reasons that we said, that reflection is not going to be affected anymore. If the moment is zero at the end, it's going to be zero everywhere else on the Z naught line, which is connected to the source. All right, so that's the second example. Okay, the moment now we deviate from real loads, there are two ways to solve the problem. We solved already one problem last time on Friday, and we said that was like a hybrid, all right, solution where, what did we do in the hybrid solution? We put, if you have a load like this, all right, here, so it's the previous example, and we're not gonna do it over, I will just remind you what we did. If you have a load like this, which is 80 R sub L minus J20, means it's capacitive, all right, has a resistor in series with a capacitor as your load, according to what I see here. Then you will need to, one way, if they allow you to use lumped elements, will be to put an inductor, all right, here, to cancel the capacitor, here, cancel this, minus J20. And then the moment you have canceled the reactive part of your load, then you can include a quarter wave transformer. So that's what we saw last time, all right? We're not gonna do this here because we wanna see stubs. So if they allow you to use lumped elements, that's the easiest solution. To use a lumped element, cancel the reactance of your load, and then use a quarter wave transformer, all right? Now, in this particular case, however, I ask you to use a stub. And I ask you, as a matter of fact, to use a series stub. All right, so these are constraints for your problem. And now I'm gonna see how I'm gonna solve this problem. All right, now we have to go, since we have a reactive load, we have to go to the Smith chart. What do we do to go to the Smith chart? We have to normalize all of the loads we know, and everything that we are gonna find out on the Smith chart is gonna be normalized with respect to the characteristic impedance Z naught. If for some reason Z naught is not given, the standard value for Z naught is 50 ohms, standard, all right? Everybody's using that as a standard. So 50 ohms, but I will give it to you, no matter what. So here, we have to go to Smith chart. You need to remember that whenever you have stubs, Smith chart is the way to solve the problem. So first of all, we normalize the impedance with respect to 50. It gives us 1.6 real part normalized minus J.4. So you know that minus J.4 represents a capacitive, all right, a capacitor rather, which is, so we say that the load is capacitive, has of course a real part. So then what do we do? So first of all, when you have to solve a problem with a stub, you also have to use a section of a line. You're not gonna put the stub right here at the end. There is no such a thing, because usually at the end, even a lumped element at the end is a bad design, because usually at the end, you're gonna have the place you're gonna make connections to the rest of your load could be an antenna. All right, so you will need to find a way to connect to the antenna. You're not going to have a stub there in the connection. It's not going to help. It's not going to work for you. All right, it's going to create problems. Usually we try the stubs to put them inside your network, not at the end of it, not at the load. We try to avoid placing stubs at the load. Okay. So you know you have to use a section of a line. Also now I give you the freedom to choose both for the stub and the section of the line the same characteristic impedance, which is enough. All right. So what are we gonna do? Let's look at this one physically before we go to the Smith chart. So we will have to take this to find where it is on the Smith chart, the normalized load. We will have to go along a section of this line until we find a place where we are gonna place the stub. Okay? And then we will have, that is gonna give us that length, D. And then after we find out where we are gonna place the stub, then we have to find out what the length of the stub is. And also if it's a short or an open. Because either one of those can give you a solution. Okay? And how are you gonna select open or short? You're gonna select the one that has the smallest, the shortest length. All right? You do not use extra lengths unless they've asked you to do that. Ideally in a design, you go for the smallest size. All right, so now let's do what I said. What do we do here? First of all, we find our load. How do I find the load normalized on the Smith chart? I'm writing the equal resistance circle, which is 1.6 normalized. So I'm writing this circle. All of the points of this circle have the same normalized real part of the impedance. And then also I have to find the circle that has all of the same imaginary parts, which is minus 0.4, minus, therefore I go below 0.4. So I'm writing this, and then the intersection of the two is my impedance at E prime. All right? That is 0.6 minus 0.16 minus J.4. Okay. Now, from there, you remember what I said? You have to move on a line, along a line, to find the place where you're going to find the location of your stub. So if you want to move on a line, there is only one circle that allows you to move on a transmission line, and it's this one, the purple one. And I call it the constant VSWR circle because that on the line, everywhere on the line, the VSWR is constant. So if I consider that my point is on this transmission line that I showed you earlier, the first section here, all right? The VSWR on this line is going to have the same value between E prime and DT prime. Everywhere on this line, DT prime, E prime, everywhere here, the VSWR is constant, and it's going to have the value that it has at this point, E prime. Now, what is the circle that corresponds to this VSWR? Even if we don't know it yet, we know the circle. All right? It's here, the circle that goes through this point. And I write it. So now I have to move. I have to move from the load, which is at E prime, to whatever point I have to stop and place the stub. So I will move along this purple line, and I will move along one particular direction that says towards the generator. Towards the generator. Because if I am at the end of the line and I move, there is only one direction to go, and that is towards the generator. All right? So then I go from E prime to DD prime. Why I stop here? I stop when I find the circle that goes through the center of the Smith chart. What does that tell me? the circle that goes through the center of the Smith chart, which is this one, that goes to DD prime, all the points on this circle, all of them, have a normalized real part in the impedance, which is 1. In other words, all of the points on this circle, the constant resistance circle that goes through the center of the Smith chart, they have an impedance, a real component in the impedance, which is 50 ohms if you denormalize, right? 50 ohms. And I like that because that's where I want eventually to find a way to reduce my complex impedance to 50 ohms. All right, the stub is going to help me do that. So I know that I have to move along this. And I have to move as long as I need to get to the center of the chart. So practically on the Smith chart, I know I have to do 2 things. Move along the constant VSWR circle from here, there, and move from DD prime to BB prime. Now, okay, I found that, but how am I going to translate those 2 movements into what I need to use in my design? What do I need to use in the design? 2 things. What do I need? The 2 dimensions, the 2 distances, D and D sub S. Now, D. How am I going to find D? I'm going to the Smith chart, and to be able, when you move on a constant VSWR circle from one point to another, from EE prime to DD prime, you can find the distance by connecting this yellow line from the center of the Smith chart through EE prime all the way until you come to the outer circle. That's where you read distances. And you read a number here, which is 0.282 lambda. You write that. Then you go to the point that you got into after you move. You connect also the center of the Smith chart, BB prime, to this point, DD prime, and then you extend this line until also you hit the outer rim. And then you read this number, which is 0.353. Okay, which means I move from 0.282 lambda to 0.353 lambda. The numbers by themselves have no meaning. But what has meaning is the difference between these 2. All right? Because this number, I mean, right here, I am at my load. So obviously, what does this mean? However, as I move from here, that is how much distance I take to go from one point to another. So the difference between these 2 is important. And the difference between these 2 numbers is here. And therefore, that tells me that I have to move on the transmission line by 0.071 lambda. And at that point, I place a stub. All right, because the stub is going to be placed at DD prime. And the stub, you remember stubs that they had either open or short? What is the input impedance of a stub? It's always reactive, no real part. All right, the input impedance of the stub has only an imaginary part, which means that if I place a stub in series on my line here, this impedance, the equivalent impedance that is going to place on the line is going to be imaginary only, which means that if at this point my impedance has a real part of 50 ohms, then the stub is not going to affect that. All right, so the stub is going to only affect, in this series configuration, the imaginary part of my impedance. So at Z input, DD prime, my impedance, let me see, my Z, if I go to the Smith chart and measure, I find that my normalized input impedance at this point, DD prime, before I place the stub, is 1 minus J.55. All right? If I read from the Smith chart. So here, where is this point? D. See, if I go here and read it, is 1, because it is on the one resistive circle, minus J, whatever I read down here, I extend the line for the reactive part and I see minus 0.55 down here. And we measure it from the innermost, okay? From the innermost, what is it, here, rim. And that is 0.55 negative, because in the lower. Okay, so that's my impedance at DD prime. So now, if I go back here, oops, what have I done? There. If I go back up here and say, now I know where I am here. When I come here, I read this point on the Smith chart and I found it to be 1 minus J.55. So if I want to place a stub, this stub has to cancel the reactive, the imaginary part of the input impedance and DD prime. So if I go down here, this is how the stub is going to impact my line. The stub is going to load the transmission line at this point on this side only with a imaginary load, reactive load, all right? And I want to design the stub so it cancels my minus J.55. I want Z sub S normalized to be plus J.55. All right? Why is that? Because when I look at the Z input at BB prime, it's going to be the series combination of ZS normalized plus Z input at DD prime. All right? It's going to be the sum of these two impedances, series combination, which means it shows it here, in fact. Which means that if I choose my Z sub S here to be plus J.55, the sum of the two, which is this impedance at BB prime, is going to be 1. So by doing that, I have now created, I have found a way to get my impedance at this point, input impedance at this point on the line, to 1. But this is like the load that this line sees. This line, the red one, does not see anything beyond that. All right? Does not see down here. It sees here, nearsighted. It sees everything that happens to it at that point. And at that point, it sees an impedance which is normalized to 1. Therefore, the reflection coefficient at BB prime is going to be 0. And it's going to stay 0 for the rest of the line. So it does not matter how long this line AA prime, BB prime is going to be. It does not matter how long. The reflection coefficient is going to be 0 everywhere, which means that this here is going to match to this. It's going to be the input impedance and AA prime is going to be 0. All right, it matched when it's matched. Everywhere the input impedance on the line is 0, which means it's going to be 0 here, and therefore it's going to match to the load. So that's how we solve this problem. Any questions? Okay, we have not finished though. We found how much the stub should give as an impedance, as a load there, but we have not found the length of the stub. So how are we going to do that? We are going back to the Smith chart. Usually, when I am solving these problems, I do two separate Smith charts because otherwise it gets so, and I suggest for you, especially since you are practicing right now, use separate Smith charts if you have to calculate the inductance, the stub or other things. Use separate Smith charts because otherwise it's going to get too crowded and we'll make mistakes. So here, what am I doing? I know how much is the load that the stub should present to the line. It's this is a best normalized. How much is that? J.55, right? So now I'm trying to find it. I'm going here to find it. I'm going here, all of the, I'm reading, and it's 0.55 is like that. Where I saw this a best normalized. Now, let's assume that this stub, at this moment, we don't know what yet of whether we're going to select a short or an open. Let's assume that we select a short. A short in impedance means that we are here at 0, all right? When the stub is shorted, it means that the load is 0 right there, short circuit. So then we will move from here along the outer ring, we'll move until we find this impedance. So we'll do the same thing, connect the center to this point and extend it, connect the center of the Smith chart to this point that is 0 and extend it, and measure how much is this distance in between the two. Here it happens to be 0, that's where the Smith chart starts at this point. And then here it says 0.08, all right, 0.08, so approximately. So this distance, which is the length of the stub, is 0.08 of the wavelength. If the stub has a short at the end. Okay. Now let's assume that somebody comes and says, "Well, could you tell me how much the length of the stub would be if you had an open at the end? How would you do that?" Okay. Well, we know what we need to see it in the entrance, at the entry point to the stub. All right. We want to see this. But if the stub had an open at the end, that means that the termination of the stub, the end point of the stub, will be at the open end here. And if I were to move from this open end all the way until I find the input of the stub, then I will have to go around all the half circle and then plus this one that we found, which was going to make the total length of the stub. The half circle is a quarter of a wavelength plus this. So it would make it 0.25 plus this, which is very long. So I will not go for that length, all right? I will go for this one, for a short. And therefore I say, okay, I'm going to go the transmission line. So that's my solution to the problem. I'm going to go on the transmission line by 0.07, what did we say? 7 or 7.1? By 0.071. So my D from here, the end, to this point, D prime is 0.071. And then I'm placing a short circuited stub. So practically then you decide that it's going to be that this is your solution. No. The other is the solution, short. And in this case, the length of this line is going to be 0.08 lambda of this stub. And then you're done. Then you've made Z input at PP prime to be 50 ohms. And then this is 50 ohms everywhere, so it's 50 ohms here, and you're matched to the load. Okay? Any questions? Yes.
So because it's a consistent, so it's the left of PP, that's why the reflection is 0. Is that just
Yes. Yes.
What is the
reflection represents the mismatch of the load to the characteristic impedance. So if the load is not 0, then you have a reflection. And usually to find the reflection at this point, the reflection coefficient at that point. So let me see here. If this were to be the reflection coefficient, all right, the reflection coefficient, then I will call it right here, gamma at BB prime. And that will be 1 minus, well, excuse me, not normalized. Let me write them in a, not in a normalized form. ZL minus Z naught over Z, in fact, even there, let me just, 1 second. You be consistent with it. Z in at BB prime minus Z naught over Z in at BB prime plus Z naught. That's the reflection coefficient. And since Z input at BB prime is Z naught, then the reflection coefficient is 0. But physically, it gives you an idea of the mismatch between the load and your characteristic impedance. Okay, any other questions? All right, now let's go to another example that we're going to solve here. I have set it up, excuse me. And we're going to solve it. Now, what happens if somebody comes to you and says, it gives you a problem like this, where everything is in admittances? All right? How would you solve a problem like that? We'll solve this problem today, and then on Wednesday, I'm gonna help you understand when to select going with admittances or impedances, all right? But let's assume that somebody gives us a problem and says, I have a load Isabel, which has a real part, like a conductance, this is 1 over ohm, and an imaginary part. So this is 1 over ohm, the units. And then I have a line where I'm giving you not the characteristic impedance, but the characteristic admittance, which is 1 over Z naught, all right? And then I ask you to place a shunt stub here. So the reflection coefficient here of the line AA prime, BB prime is 0. So what you need to remember, and then I will move the Smith chart to the next page. Let me see, let's make some space. All right. Got. Paste. All right. So what we need to remember, let me write here first. 1. Y naught is 1 over Z naught. All right. Number 2. YL is 1 over ZL. So in fact, here also, Y naught normalized is equal to 1 is equal to Z naught normalized. All right. When I normalize, in fact, admittances, I normalize them with respect to the characteristic admittance. When I normalize impedances, I normalize them with respect to the characteristic impedance, all right? So you need to remember that, and I'm writing in here, So the normalized Y naught is with respect to the characteristic admittance. The normalized Z naught is with respect to the characteristic impedance. And that's why they both give 1. All right. Now, YL equals ZL. So that implies, before I do anything else, that if ZL equals R sub L plus J X sub L, then your YL is not the inverse of each one of those. I'm saying that because I have seen many students making that mistake, is this inverse. All right? It's not the inverse of 1. It's not. It's not 1 over RL plus J 1 over X sub L. I have seen this mistake numerous times. So it's not that, all right? You need to remember this. So if you want to find it, you have, if I don't give you YL, but I give you ZL, but then you want to use YL, you have to invert the whole complex number, ZL, all right? So that is. Now, when I normalize a YL, I normalize it with respect to Y naught, not Z naught, obviously. And therefore, I will have, since I wrote this in this form, I wrote it. I will have that this is going to be GL over Y naught plus J BL over Y naught. And as a matter of fact, let me just remove that from here. So you see how I'm finding the normalized version. And then if I call this one normalized GL, and I call this one normalized BL, then in this case, YL normalized equals GL normalized plus JBL normalized. So in this case, I have that, all right? But admittances are normalized with respect to characteristic admittance. Impedance is normalized with respect to the characteristic impedance. For up today, I would say you will have to be very careful not to mix up normalized impedances with normalized admittances on the same Smith chart unless you transfer an impedance to admittances. And I will show you how to do it next time. So my advice is either you use the whole circuit to be in the Y form, in the admittance form, but don't try to go arbitrarily, Z here, Y here, and then Z there. And then use Z to normalize Y, all right? Remember that. You cannot normalize an admittance with an impedance because admittance has 1 over ohm, impedance has ohm. You cannot divide admittances with impedance. You have to be careful, all right? The next thing, what you have to remember, while in impedances, so a series combination of 2 impedances. So say Z1 and Z2, it's equivalent to 1 impedance, Z3, where Z3 equals Z1 plus Z2. The equivalent to that, as they say, the corollary to that is admittances, but to some admittances, they have to be in parallel. So don't use 2 admittances in series and you add them up. This is equivalent if this is Y1 and this is Y2. This is equivalent to one admittance, Y3, which is Y1 plus Y2. All right? So these are what you have to keep in mind as we are going to try to solve this problem. And that is for a simple circuit theory, plus the normalizations that you have to keep in mind. Okay. Now, when you have everything in Y, and you normalize everything with respect to Y naught, then you can use the Smith chart as the same way we use it for impedances. Same numbers, same, you look at the, you read the same kind of thing, all right? So you use it the same way. Now, let's therefore give it some values to these admittances. Okay, and here they are. I am giving you that the load here, YL, is, you see how small the numbers are? Because that's how admittances are small numbers. You remember that, all right? Impedances are big in ohms, admittances are small in 1/ohm. So if you see that I give you 100 in admittance, it's a mistake. Or if you find through your calculation something like 100, 150, and it's in admittance form, then there is a mistake somewhere. So small numbers. Now I have to go and normalize that with respect to Y naught. For a standard line, which has Z naught to be 50 ohms, how much is Y naught? 1/50. All right. So Y naught is this small number, 0.02, 1/ohm. So if I want to take this YL and normalize it, I have to normalize it with respect to these small numbers. So then it gives me reasonable results. It gives me that YL is 0.5 minus J to 1.75. Now we are going to use the Smith chart the same way, negative below, positive above. However, when you translate these numbers into physical elements, you have to remember that this is an admittance. Okay? So my question to you is the following. If I have an admittance like this one here, can you look, when you look at this, can you tell me what kind of circuit configuration that would be? I'm asking you, say, to translate that into an RLC. What kind of a load is this? What kind of configuration would it have? Think. Yes. First of all, you have to remember, you have to decide how you are going, if you split them, if you split the real and imaginary parts in conductances or resistive conductances, and then the other inductor or capacitor, the other one, you have to remember what a plus means in admittances. What is a plus? When do we sum up to admittances? When they are in here, in parallel. All right, remember that. So it's not going to be one plus something, it's not going to be a series combination, it's going to be a parallel combination. Okay, so YL practically is going to have a conductance and it's going to have a reactive part. And how is this going to be? It's going to be the parallel combination, therefore, of a conductance and then with another reactive part, I have to figure it out what it's going to be. That's how it's going to be. All right. So this is going to be my GL. This is going to be my BL. This is what gives me a plus. All right, you sum them up. BL, what is it gonna be? A capacitor or an inductor? You said it doesn't matter before.
Oh,
It's an inductor, all right? Why is that? It's gonna be, therefore, if I were to write it here, this would be practically combination of these two. Why is that? All right, let's try to write everything in inductive, in an admittance form. So this is gonna be a GL, and GL is the inverse of RL. All right, but I don't need to put RL there. I don't care because it's parallel. Therefore, why would I put impedances when I have a parallel and I need to sum it up? I'll leave it as admittance. However, B sub L in this form here is minus something. So this one here, my B sub L, is minus a number. All right, so practically my J B sub L is going to be a minus J, and therefore the only way that a lumped element can give me a minus J if it's an admittance is this one. All right, and therefore this is L, if you want to write it like this, and this is R. If you want to find, therefore, the admittance of this, if you were doing all the calculations to find the admittance, you would find that the admittance to this is GL, which is 1 over, so this is 1 over GL, all right? That gives minus 1 over J omega L. That's what it is, all right? Why? J omega L is an admittance, is not in ohms. 1 over J omega L, I should say. 1 over J omega L is 1 over ohm. All right? Because J omega L is always in ohms. So 1 over J omega L is in 1 over ohm. And therefore, because we bring the J into the numerator, the J becomes minus J. All right, which in fact forces my B sub L, that I call that, to be negative. So you need, what I would like you to do is please go back to circuit form and then review this, because I want you to have that very clearly so you don't get confused when you have admittances at some point in your design problem. All right, you know how to handle them. Okay, so we'll continue with the solution of this problem on Wednesday. Okay, thank you.